Hey, good morning, Winsburg, or that's kind of a weird way to refer to you. I don't know, but at least it's morning right now where I'm at, or when I'm recording this. So welcome to a brand new chapter. Last chapter we talked about ketones and aldehydes, and here we're still talking about carbonyl compounds, of course, carboxylic acids and their derivatives. That's what is on the table here. And you would imagine the chemistry is going to be a little bit similar to ketones and aldehydes, and you would be right, because all these are carbonyl compounds. The main theme still is going to be nucleophile adding to the carbonyl carbon, okay? Where the only difference is X here now is going to be some sort of a leaving group, and so that's going to be a little bit of a difference there, as you'll notice, and we'll get into that. But first, just to review the preparation of carboxylic acids, I'll maybe would have you try to think about how to do this because this would be a review. I think this is from chapter 12 material. And then, let's see. The only things that you may not have covered, we may not have covered in chapter 12, I believe it was 18, the aromatic chapter. Remember that if you have something like this, or even like that, as long as the benzylic carbon, which is that carbon, maybe, hold on, benzylic carbon is that, as long as that is not quaternary, as long as that carbon has hydrogen, at least one hydrogen, then you can oxidize it to the carboxylic acid, right? Remember, and then all the carbons fall off. We could also do ozonolysis of alkyne. So that would be, if we wanted to make this molecule here, then we would have to have 1, 2, 3 carbons. So this would do it. And remember, this type of ozonolysis, the difference between the ozonolysis where you use reductive workup, dimethyl sulfide, is you just do an aqueous workup, so it just ends up being more oxidative in the end. That's why you get more of an oxidized functional group, carboxylic acid, and then not an aldehyde. You know what, since I've done so much of the review here already, I might just fill in the blank for you. But before I fill in the blank up here and whatnot, maybe pause the video and see if you can fill in the blank now. Okay. So you could make it from this alcohol with that reagent, or you could make it from the aldehyde with the same reagent. So that would be the same deal. Oops. Over on the other side as well. And yes, I know how to use my iPad pretty well. Praise the Lord. So that's kind of hopefully just a review for you. And this down here was chapter, sorry, I forgot. I think it's 9, the alkyne chapter, and then this was 18, I believe, if you need to refer back to your notes. There's other ways that we have talked about, and that is the hydrolysis of nitrile, and we'll discuss the mechanism for this later. But if you treat a nitrile with strong acid, and usually heat is required because it's hard for water to add to this carbon. Okay, so that's the brief mechanism there, but that's that's a synthetically useful maneuvering that chemists would use. So it would be good for us to be aware of that. It's not as important, but the byproduct, of course, will be ammonium ion here. Okay, and what I want you to get for now is that because we haven't talked about the mechanism and whatnot yet, how the reaction works, but what's important is this is a really useful synthetic tool, because if nitrile group can be turned into a carboxylic acid, that would present a nice way of adding a carbon from the nitrile cyanide. So adding this carbon and then turn that into a carboxylic acid functional group. That's very convenient. So if you do these two reactions on this benzyl chloride, first, I guess I don't need to put it in a bracket because it's not the intermediate, like in a mechanism per se, but first you get this, or maybe I'll put it in just to, maybe that's less confusing. So first you would get nitrile, and then that would be hydrolyzed to give a carboxylic acid. And notice you have gained a carbon, and that process in the biz, so to speak, is called homologation, because you're adding onto the chain like another of the same atom. That's why it has the prefix homo, which means the same. So we homologated this benzyl group. If you're at a conference, scientific conference or something, oftentimes scientists won't like use everyday English language to talk about something like, you know, we added a carbon here. That sounds very not professional. So we might say we homologated this benzyl chloride with a cyanide. But another use of this, remember, cyanohydrin is a thing. So if you have a carbonyl starting compound, you could make cyanohydrin, and from there you could do hydrolysis to get to the carboxylic acid. So hopefully that makes sense to you. And then again, I didn't maybe encourage you to pause the video, but stuff like this, it's good to see if you can fill in the blanks, okay? How else can we make carboxylic acids? Wait, I just noticed I messed up with the alphabets. Okay. I am usually pretty good at the first 4 letters or so of the alphabet, so bad mistake here. But here's a new reaction that we actually haven't seen before, and that's the use of organometallic reagents and carbon dioxide. It's kind of a fun reaction in that you have to bubble in carbon dioxide into the reaction mixture through usually like a balloon or a gas regulator attached to a gas tank of carbon dioxide. And we can indeed make carboxylic acid. It's kind of like hydrolysis of nitrile type of strategy. You do add a carbon as you would introduce a nitrile, and then you do add a carbon as you introduce carbon dioxide, being this carbon here. And so how would the mechanism go? Typically you start with something like a Grignard reagent, right? Or organolithium reagent. Both of these are very nucleophilic carbons. Oops, that N looks horrible. And with that, you could see a reaction that happens like this, because carbon dioxide is essentially like a carbonyl compound, right? It's like you have double carbonyls on the same carbon, so you can imagine that there is electrophilicity of this carbon. It's partially positive, and so once a nucleophile adds, this would happen. Of course, this is your new bond you just made, the new carbon-carbon bond, so it's synthetically very useful. This is the product of the reaction. Usually you follow this up with an acid aqueous workup so that you can protonate that carboxylate anion, which will render you the carboxylic acid product. Same idea. if you have the organolithium, you use, of course, these two same electrons to do the same mechanism, and that would happen as well. So here's some examples for you. Maybe it would be a good time to pause the video and see if you can fill in the blank here. And so hopefully you pause the video. So to make this benzoic acid, remember this is benzoic acid, hopefully you remember that name, we need to, so we are adding this carbon dioxide. So this is that carbon, okay? Carbon dioxide is that carbon. And before that reaction takes place, we needed to have a phenyl magnesium bromide or a phenyl Grignard reagent. So to make that, of course, you need to treat the phenyl halogen, phenyl halide, something like this, with magnesium ether, and then you can make the Grignard reagent. So that's the first step. And then the second and third reactions there would for the benzoic acid product. Okay, hopefully that makes sense to you. And then let's think about another synthesis problem. So here we have yet another situation where we might be adding a carbon here, right? So how do we do that? Well, likely we're talking about adding that as either a nitrile or a carbon dioxide, right? So, because those are both ways that would add a carbon. So how do you know which is which? So if we were adding this as a, this orange colored carbon that I marked, if we're adding this as a cyanide, right, this carbon has to be a nuclear electrophile. When I say this carbon, I'm talking about this carbon. And then the cyanide adds as a nucleophile. Or the other possibility is that this is going to be some sort of a nucleophilic carbon, and that adds to the electrophilic carbon dioxide. So the question in designing the synthesis would be, this is like a puzzle, logical puzzle thing here. Would it be easier to turn, maybe let me erase this. Would it be easier to turn this carbon that I just marked as into an electrophile or nucleophile? So that's the question. And if we want that to be an electrophile, we would use cyanide. And if we want that to be a nucleophile, and that would be easier, then we would use carbon dioxide in the last step. And to be honest, to be fair, like either is kind of possible, but if typically for a reaction like this, you would have some sort of like a leaving group, right? Where the nucleophile attacks and whatnot, unless we're trying to design an SN1 reaction. And you might wonder, can we do this type of chemistry where hydrogen adds to the double bond or a proton adds to the double bond, and then you make a carbocation, and then cyanide adds. And that's not an unreasonable idea, except that remember, to add a proton across an alkene double bond, you need a strong acid, and your Gen Chem should have taught you that this is not a strong acid, a cyanic acid, right? That's not one of the strong inorganic acids, so that process probably will not work. So for that reason, we're probably not going to do this approach. Okay, so we're gonna go with the other approach, which means that the very last two steps in the synthesis likely will be that, okay, which means we needed to have this Grignard reagent. Okay, and another problem, of course, with the first approach is if you have a tertiary halide at this orange marked carbon, you can't do SN2 approach, right? So, because SN2 never happens on an tertiary substrate. It's too sterically hindered. So, to make this Grignard reagent I just mentioned, you would indeed make it from this bromide, but I want you to understand that you can't do this. That will not work, right? No SN2 on a carbon there. So like you can't do, just to be more explicit, you can't displace that bromide with a cyanide and then follow that up with acid hydrolysis. You can't do that. That won't work. Okay. So now the question is, how do you make this tertiary bromide from alkene? And that would be a Markov-Markov reaction. So that would do it. So hopefully that makes sense to you. Since this is a good stopping point, I'm just gonna make this just the first half of the Wednesday lecture. So I'll see